Okay, good morning. So let us continue the last lecture a little bit because there are many things we have to cover from the previous one, and then hopefully we can go to the new one today. I have also put so this is the old one. Okay, so one thing I want to talk about, I didn't talk about at all. So sometimes they are asking you to solve a logarithmic equation. So for example, you are supposed to find x. Okay, so you need to know the rules of the logarithm, and then try to isolate x somehow. So, for example, one thing we can do, we can collect the left-hand side into one log. Okay, and of course you know that you can raise these two on top of that, and then there will be a difference between two logs. Then you can write as the log of the quotient. Yes. So let us do it in one step. So if I do that, then the problem becomes the log of x plus 4 divided by x plus 1 squared to the same base. So what I am telling you is that I am allowed to write the left-hand side in this form. Okay? And the right-hand side, I keep it as 1 over 2. Yes? Is that clear for everyone?
How come it translates to that?
So there are some formulas that hopefully you can see here. So I am using which formulas? For example, here I am using this formula. Which one is that? Yes, this one. So you see this number on top can move to the back, or if this is in the back, I can move it on top. And then I have the logarithm of x over y. I can write it as logarithm of the numerator minus the logarithm of the denominator. So I am using these two properties together to write it in this form. And then how can I continue? I would say that logarithm of a number, which is still I don't know, is equal to 1/2 to the base of course 4. What does it mean? It means this number raised to that number is equal to this number. So this means that x plus 4 divided by x plus 1 squared is equal to 4 to the power of 1/2. But then it becomes x plus 4 divided, I raise it to power 2x squared plus 2x plus 1. On the right hand side, 4 to power 1/2 is just simply 2. And then I will start solving this equation, so I multiply this here. And then I get x plus 4. And then, for example, I can write 2x squared, and I move this to the other side, 3x minus 2 equals to 0. And then, of course, I will solve this equation and find the answers. But one thing that matters, I don't want to continue it because I want to go a little bit faster. Is everything here understandable? Okay. But then when you solve this one, for example, let us use ABC formula. So it's minus 3 plus or minus the square root of this number to power 2, 9. And this one is 16, so it becomes 5 at the end, yes? And then divided by 4. So this is 9 minus 16, that's correct. So I will get two answers. One answer is 2 over 4 is 1/2, so x becomes 1/2. Yes? And then the other one, x becomes minus 2. Okay, one thing that I want to mention, you have to be very careful here, because for example, you can see that this is not indeed a root for the original equation. This is called a false root. Why this is not acceptable? So it is not acceptable because a solution to an equation means that if you replace x in the original equation with that x, the left-hand side should be equal to the right-hand side. But I hope that you can see I am in trouble. If I replace x with minus 2 here, this becomes logarithm of 2 to the base 4, no problems. But if I replace x with minus 2, then I will have a logarithm of a negative number, which is not even defined. Is that right? So when you are solving a logarithmic equation, you might get a false root at the end, so you have to be careful that this answer is not acceptable. Why this happens is because I am going in that direction. In that direction, everything works fine, and I am getting these answers. But in principle, I am not solving the original equation. I am solving this equation. Why this happens? Because the formula, for example, let us make it a little bit simple. When I write logarithm of x to power 2, people usually immediately write it as 2 log of x. But the formulas that I have mentioned up there are some conditions on top. You see, there are many conditions. If those conditions are not met, there is no guarantee that these are correct. For example, this formula is not always correct, because in this case, it is also allowed to have negative value for x. No problem happens. If I have a negative number to power 2, it becomes positive, and the logarithm of positive is correct. But if I have a negative number here, that's wrong. So in principle, logarithm of minus 2 to power 2 makes sense. Because minus 2 to power 2 is 4, logarithm of 4 makes sense. But if I naively use this rule and make it this one, of course this is correct. This is not correct because the left-hand side makes sense, the right-hand side is not even defined. So this equality does not hold. Yes?
So if we started our initial equation with, instead of 2 log base 4,
yes,
it would just be log base 4 of x plus 1 squared.
Yes.
If the initial equation started like that, then minus 2 would be a root, right?
Yes.
Yeah.
Yes, that minus 2 will be the root, as you see here. Yeah. So the problem is that sometimes people say that, okay, I am not doing something wrong, why I end up with something wrong? The reason is that in principle you are not solving the original equation, you're solving this equation, yes? So for this equation that's a root, but not for the original equation, because you have to respect the rules as well. So whenever you are solving a logarithmic equation, always be aware of this danger that might be the answer that you are getting is not an acceptable answer. Okay. Okay, so let me start the next part of the lesson. So do you remember we talked about a function, the exponential function, f of x equals to a to the x. And then I told you that for an exponential function, we always assume that a is positive and a is not equal to 1. So one important question regarding this exponential function is that what the derivative is. Okay, so if I want to know what the derivative of this function is. Okay, the only thing that I have at my disposal is the definition of the derivative. So if I want to calculate the derivative of f, I should calculate the limit of f of x plus h minus f of x divided by h goes to 0, if I can manage to find this limit. Okay, I just want to give you an idea because doing it properly, it's a little bit different from this way. So if I want to calculate this, f of x plus h means I replace x with x plus h. So this becomes a to power x plus h minus f of x is my function itself. And then divided by h goes to 0. So the problem is that I have to calculate this limit, okay? So this limit is a little bit problematic. I just want to give you the idea. So between these two, I can factor a to power x out. Then I will have a to power h minus 1 divided by h goes to 0. Yes, is that understandable? If you multiply this back, a to the x times a to the h, the bases are the same, exponents will be added, so that's correct. A to the x times minus 1 is that's correct, okay? But this one is a constant. Constant because the limit, the variable of limit is h. So I am sending h to 0, so I am not touching x. X is already fixed and it is fixed now. So this means that I can write it as a to power x, which is a fixed number as far as this limit is concerned, then multiplied by the limit a to the power of h minus 1 divided by h goes to 0. So this means that if I want to know the derivative of the exponential function, there is one question I have to answer, and that is how I can calculate this limit. So if you don't mind, let me call it L. Still, I don't know what L is. But I know something. I learned that if f of x is equal to a to power x, then I learned that the derivative of the function is not that different. It is the same function multiplied by a constant. Okay, but the point is that still I don't know this limit. Okay, so the way we have to do it, there is a number. So I just want to motivate you. I'm not going to prove anything. So for example, if I choose a to be if I choose a to be 2, so here for this limit, let me choose a to be 2 and let me choose a to be 3. And then I will face two limits. Instead of a, you put 2. And then you have another one. Okay. So I just want to motivate you. I'm not going to prove anything rigorously. So take your calculator, for example, and put smaller and smaller numbers for h, and calculate using your calculator what are these numbers. Then you will see that, yes?
Why do you pick 2 and 3?
Just wait, okay? So you take your calculator, make h small, and then put the small values of h here and calculate them. You will see that there will be not very nice pattern to see what is going on, but something becomes relevant, clear, that whatever those numbers are, they are always less than 1. Okay, so I'm not claiming that is a good way, but I just want you to feel what I mean. So if you take your calculator, calculate this fraction with the small values of h, you will see that there is nothing very nice pattern reveals that you can guess what is the number, but you can see all of them are actually less than 1. And if you do this, the same strategy, if you do this, then suddenly you will see that all those numbers now become greater than 1. Okay, so this might motivate you. You see, if I choose a to be 2, this corresponding limit becomes a number less than 1, and if I choose this, this limit becomes greater than 1. Okay, this is my presentation, but I'm asking you one question. Do you think there is a natural question? I'm just emphasizing on the word natural. Okay, somehow. Do you think there is a natural question now? After I said this, is there any natural question comes to your mind? If I choose a to be 2, this limit for 2 becomes less than 1. And if I choose 3, this corresponding limit becomes greater than 1. I'm not forcing you that this is always the case, but do you think there is a natural question to ask yourself now?
At which number does it equal 1?
Yeah. So the question is natural. So that's what I'm saying. I just want to emphasize that this is naturally coming out. So it means that is there any number that I can choose, and for that number this limit becomes exactly 1, because I know if it is 2 it's less than 1, it is 3 it's greater than 1. The natural question might be is that is there any number that I can choose and this limit turns out to be exactly 1. I don't want to prove it for you, but the answer to this is yes, and that's a very fundamental constant in mathematics, and that is called the Euler number. Okay, so and the Euler number is denoted by little e for Euler.
I guessed it right.
Pardon? Yes. So this means that e is the number which makes this limit equal to 1. So this is the definition of e. If you want to know, e is the definition of e. One definition of e, if you like, is e is the number that makes this limit equals to 1. Okay? So of course, if you want to know a little bit about this number, then of course you can say that for a small h, if h is a small, this is approximately equal to 1, if h is a small. And then what happens, I multiply by h, move this to the other side, and raise both sides to power 1 over h, then e becomes approximately if h is a small. And if you want to know how much this number is, you can take your calculator and calculate it for smaller values for h, and this will be 2.72. And of course, this is an irrational number, so this means that these decimal places will go forever. So it's like pi. Pi is 3.14 something. E is the Euler number, which is 2.72. But we never work with the number, with the exact value of the number. We only work with the symbol. But this is just a simple number. It's a very important constant. Yes?
I think it's better if you write it 2.718.
Yeah, I mean, this is better, yes. Okay, so now this is one important thing, but here you want to calculate the derivative of exponential functions. For one particular case, we know the answer. What is that particular case? Because if I choose a to be e, I will be able to do the same calculation. So it will be e to power x times the limit of e to power h minus 1 divided by h, which is equal to 1. So this is a very simple fact that the derivative of this particular function, this particular exponential function, the derivative of it becomes exactly itself. Okay? But now I can go and so let us go a little bit in a different way. So this is E. I was not able to answer this question yet. I didn't answer what is the derivative of the most general exponential function, but I was able to answer it exactly for one particular case, and that is the case where the base is E. In that case, the derivative is exactly equal to itself, but we also know something like this. Let me write it here for you. For the general case, the only problem is that what is this number? Okay. And then, of course, immediately, let me write another formula for you. If you have e to power u, and I want you to take the derivative, if u is a function of x, okay, so that's something simple. So this is the chain rule. So what is the rule? You can pretend that u is x. So the derivative of e to power u becomes e to power u itself. But because of the chain rule, you have to multiply it by u prime. Yeah, is that right? Okay. So now, there is because this question somehow was natural, there is a logarithm whose base is that e, and we call it the natural logarithm. So, okay, so let me write here the natural logarithm. So, natural logarithm is if I have x, a real number, this means belongs to real number, but positive. If you see ln of x, you read it as the natural logarithm of x, or just simply ln of x. If you see this symbol means logarithm of x, whose base is exactly that Euler number e. Yes? So that's the definition of the natural logarithm. So there was a number that naturally came into our discussion. That number, we called it the Euler number, and that is that number. That number is greater than 1 and it is positive, so it can serve as a base of a logarithm. So if I have a logarithm whose base is e, instead of writing this, I just symbolize it by ln of x, and it is called the natural logarithm of x. So be careful. So this should be. So now, because ln is a logarithm, it will enjoy all properties of logarithms. Okay, for example, do you remember we had logarithm of 1 to base a, any base, it was 0. You can translate it to ln of 1 is equal to 0. Because ln of 1 means logarithm of 1 in the base e, which is 0. For example, do you remember we had logarithm of a to its own base? If a is positive and not equal to 1, it was 1. Yes? What can I write? What is the corresponding of this formula here? What is the counterpart of this formula here? ln of e is 1. Because ln of e means simply what? Logarithm of e to the base e. Okay, so for example, if x and y are positive, then what I can say, ln of xy is equal to ln of x plus ln of y. Yes? Because this is the logarithm. Logarithm of a product is the sum of the logarithms. For example, can you tell me what is the answer to this?
1.
No. So you should compare it with this very famous formula. A to the power of log of x to the same base. If a is raised to a logarithm whose base is also a, you remember we talked about this yesterday. The answer becomes simply x. So this is indeed e to the power of logarithm of x to the base e. So according to the formula, it becomes x. That's very important. E to power ln of x is just simply x. Okay? So I have written these formulas here for you, but I hope that you immediately can convince you. So all these formulas that you can see here are actually counterparts of the formulas that you had in the previous table here. Okay, so a little bit. So for example, this is also a very famous relation. Do you see why this is correct? So for example, logarithm. Do you remember I told you that if you have a logarithm of a to base b, you can go to any base that you like. For example, I can choose a base c and go to base c by writing logarithm of a to the base c divided by logarithm of b to the base c. So now, if I choose c to be e, what happens? Logarithm of a to the base b becomes logarithm of a to the base e divided by logarithm of b to the base e. But logarithm of a to the base e can be written compactly as simply ln of a, and this can be written as ln of b. So it is very nice. If you have logarithm of a to the b, you can write it ln of a over ln of b. Okay? Okay, so let us solve this example. We want to find x. 2 to the power of x plus 1 is equal to 3 to the power of x. So you want to find the value of x. Okay, so you see that your unknown is in the exponent. Whenever this happens, you need to remember about using logarithm. The base you use for solving it doesn't matter. You can choose 10, you can choose 2, but I mean, I would prefer always to use natural logarithm. So, for example, I would say that this means ln of this expression is also equal to ln of this expression. Because if they are supposed to be equal, their ln's should also be equal. Okay? And then there is a rule. If there is a power here, this power can be moved to the back as a factor. So it becomes x plus 1 times ln of 2. And here, this goes here, it becomes x ln of 3. So ln of 2 is a number. It's a fixed number. I don't know the value. If I want to know the value, I can use my calculator. But the important thing is that your unknown is x. So I multiply this number inside, so it becomes x ln of 2, and then it becomes plus ln of 2. On the right hand side, I have x ln of 3. My unknown is x. I have to isolate it on the left side. So I move this to the other side, and I move ln2 to the other side. And then what should I do here? I can factor 1x out. This becomes ln of 2 minus ln of 3. And on the right hand side, I will have minus ln of 2. So in principle, if I want to find x, it becomes the right hand side divided by the left hand side. So you can keep it like this because that's not possible to simplify it that much. So if you don't want, let me multiply it by minus sign. Then this will be flipped. If you want, you can write it as ln of 2. You can write this as ln of 1.5 because I can write it as ln of 3 over 2. And then using this formula, if you want, you can write it in form of 1 logarithm. It doesn't matter. I think if you keep it like that, that's also okay. So this becomes logarithm of 2 to the base 1.5 or something similar. Okay? Any questions here? Okay, now let us go back and answer this question, but in a little bit different way. Okay, so how can I do that? Do you remember what was the question? The question was that if I have f of x equals to a to power x, I want to find its derivative. But now suddenly I changed my strategy. I use that strategy to motivate you about the number e. But now that we know the derivative for this exponential function, by introducing you the natural logarithm, we can also calculate the derivative of this without going back and use definition. How can I do that? I will rewrite this function in the form that instead of having a as the base, I want to write it in a way that e appears as the base. Can you do that? So I want to keep x up there, but I want to write a in a form that e appears. So can you tell me? It's on the board. Somehow.
E to the power of the natural.
Yes, e to power ln of x is x, so a becomes e to power ln of a. So instead of that a, I put e to power ln of a. Is that right? But now there is a rule. This is a power. I am raising it to another power, so these exponents will be multiplied. So it becomes e to the power of ln of a, which is a fixed number, multiplied by x. So this function can be rewritten in this form. But can I now take the derivative? This is on the board. If e is raised to power u, u is a function of x, then according to this rule and the chain rule, the derivative is just the function itself, but multiplied by the derivative of the exponent. So if I ask you, what is the derivative of this function? In your head, you can give the role of u to this guy. So f prime of x will be e to power u. So I copy and paste it. But it is not finished. I have to multiply it by the derivative of the exponent. Okay, now help me to continue. Do you agree that this one can be still written in the form of a to power x? That's the same thing, yes? Instead of a to power x, I wrote it in this way. I used it. Now it is finished. I put it back into the original form. But what is the derivative of ln of a times x? What is that derivative?
Just
ln of a. Because x is just x, this is a constant, like 2x. What is the derivative of 2x is 2. What's the derivative? It's just ln of a. Yes? So this means that we found the formula. So if f of x is equal to a to power x, then what happens? The derivative is the function itself, but multiplied by ln of a. In the case that a is e, it will be e to power x times ln of e, but ln of e is 1, so you get the same formula back. But if I want to use the chain rule, if I have a to power u, u is a function of x, then what happens? The derivative, the function repeats itself, multiplied by the ln of the base, but because of the chain rule, I have to multiply by u prime as well. Yes, is that clear? Okay, now one interesting thing happens. So we were able to calculate this L. Can you tell me what that L is? ln of a. Yes, because you realized that if f of x is a to power x, using this method, I was able to calculate f prime of x to be a to power x times ln of a. But in the beginning of the lesson, we realized that the derivative of this function is L times a to power x. So now, if you compare these two, so you can immediately realize that L, which was the limit of a to power h minus 1 divided by h goes to 0, is actually ln of a. Of course, you don't need to remember that. Later we will learn some method called Hubitel's rule. We can immediately calculate them, so that's not a hard thing to remember. Yes?
should we be using the Hubitel's rule
Yes, you can.
But the derivative has that definition.
Yes, I agree with you. It's a circular loop. Yes. In principle, mathematically speaking, we cannot. Something like this should be done. Yes. And the real proof of this goes from squeezing theorem, actually. Yes. So, but you are completely right. That is not for this particular one. But if it is given in the exam to calculate the limit, you can just simply calculate them. Okay. And then what I want to continue, I think we have to go to the new lesson now, but before doing that, let me also talk about the derivative of the logarithm. We haven't talked about this. Okay, so if you don't mind, let me start with this very simple question. If I give you this function, and I ask you what is the derivative of this function? Okay, we want to answer this question. Okay, so let me write this y equals to ln of x. And I want to find y prime. Okay, so do you know what to do?
Inverse function.
Inverse function is better. Of course, in principle, you can write a definition and try to calculate the limit, but this is much safer here. So what do I do? Y, this means what? E to power y is equal to x. And I start differentiating both sides with respect to x. So this means that I take prime, but prime means with respect to x. Yes? Okay, can you help me now? The right hand side is clear. X, differentiating it with respect to x is y. But can you help me to write this? You see that the formula is on the board, yes? E to power a function of x is the derivative of this is the function itself, so it becomes the function itself, but I have to multiply it by the derivative of y. And the question mark is this y prime. So this means that, and I am on the safe side because e to power y is never 0, so y prime becomes a 1 over e to power y. This is not wrong, but this is not very natural, because if I give you a function which is in terms of x, you expect at the end to get the derivative in terms of x. But this derivative is in terms of y. If I want to write it in terms of x, you can see one step before, e to power y is x. So I can replace it with x. So the answer becomes so simple, 1 over x. But of course, when I talk about the derivative of ln function, I have one implicit assumption. The implicit assumption is that, of course, x should not be negative, because otherwise this function is not defined. So what I can summarize is that if x is positive, the derivative of ln of x is simply 1 over x. Yes? And whenever you have a formula for the derivative, you can use the chain rule. So can you tell me what is the derivative of ln of u if u is a function of x? It follows the same rule as if u is x, but you have to multiply by u prime. When you multiply by u prime, instead of writing u prime here, I prefer to multiply u prime in the numerator. And I get this one. So that's a good pattern, but this under the condition that whatever u is positive. But there is also something nice. I want you to together calculate it. If you want to calculate ln of absolute value of x derivative, let us see what is the answer. That's good to know. This is a little bit better than the original one, because for the original one I have to restrict myself to positive numbers, but here I have to restrict myself only so that x is not 0. Because if x is positive, this makes sense. If x is negative, it also makes sense. It does not make sense if x is equal to 0. Okay, so that's a little bit better. But let us see if there is any formula for this. So I can consider two cases. If x is positive, then ln of absolute value of x prime is exactly equal to ln of x prime. And the answer becomes 1 over x, as we learned here. But if x is negative, can you help me now? If x is negative, what happens? If x is negative, then I can remove the absolute value and write ln of minus x prime. Yes? But now I use the chain rule by giving the role of minus x to u. So the derivative becomes u itself, but multiplied by the derivative of u. So then what happens? This becomes minus 1 divided by minus x. But again, minus signs are cancelled, you get 1 over x back. Yes? So you see, ln of absolute value of x, in both possible cases, the derivative is the same function 1 over x. Okay? So this means that this is a better formula to remember, especially when we go to calculating integrals. Okay? So what we can do is to write this formula now. If x is not equal to 0, then ln of absolute value of x prime is just simply 1 over x again. Again, the chain rule tells me that if u is not equal to 0, ln of absolute value u prime is u prime over. Yes? So what we learned how to differentiate exponential functions, and we also learned how to differentiate natural logarithm functions. There is one question to answer: how can I differentiate another type of logarithm? So for example, if I ask you, can you differentiate this? What do you say? Change base, yes? Instead of writing this, I can write it as ln of x divided by ln of a. But this is just a constant, so you can view it as 1 over this constant, which is another constant times ln of x prime. I don't want to use the quotient rule. And then it becomes 1 over ln of a times ln of x prime. But we just learned that this is 1 over x. So this becomes 1 over x ln of a. So we learned that if x is positive, logarithm of x to the base a prime is 1 over x, but multiplied by the natural logarithm of the original base. So I have written all these formulas for you in the notes, so if you want to have them in one place, you can have them, yes? So you can do them here. Okay, if you don't mind, let me somehow summarize So, for example, let me take 1 or 2 examples here. The first example, I have intentionally wrote it in that way for you, so I just want you to feel the difference. Can you see the first question here? So what is the derivative? If I have y equals to x to the power of 2 minus 2 to the power x. So if I ask you what is the derivative, can you tell me? The formulas are still scattered on the board. So this one is the power function, which was very elementary. So the derivative of this one is 2x. But the derivative of this one is on that board, on the box. So it means that it becomes minus 2 to the power of x. The function repeats itself, but I have to multiply by an extra ln of 2. So that will be the derivative of this function. Let me solve one more for you. So for example, y is equal to ln. I'm going to solve number 4, x squared plus 1 minus x. So if I want to differentiate this, what should I do? I have to use this rule. Yes? By giving the role of u to this guy in your head. So this becomes u prime. I'm using that formula. Divided by u itself. You see, u prime is divided by u itself. But I have to continue until there is no prime left. But that is very elementary now. I copy and paste the denominator. The numerator, the derivative of this one, I am using this formula. So it becomes, now I give the role of u to this. So it becomes x squared plus 1 prime divided by 2 square root of x squared plus 1 minus 1. The derivative of x is 1. Okay, but this becomes 2x. 2 and 2 are cancelled, so it becomes x divided by square root of x squared plus 1 minus 1 divided by square root of x squared plus 1 minus x. This can be simplified a little bit. Of course, differentiation is finished, so I can take a common denominator here. So this becomes x minus the square root of x squared plus 1 divided, let me factor a minus sign out and swap them. The reason I did that, because then I can cancel this one with the numerator up there, and the answer will be minus 1 over square root of x squared plus 1. So the derivative of that function is equal to this. Okay. Because there is no time, I have to skip a little bit because I want you to definitely see at least the theorem itself. So that's very important. These are questions you can do. This is an exam question. This you shouldn't have any problems. This is implicit differentiation, but of course exponential and logarithmic function involved. Okay. One thing I want you to know, it's good for the solving problems in this workshop, is the growth properties of exponential and ln. And this is mentioning that if a is a positive real number, then we have these formulas. Okay, and I think, might be it is hard, I am summarizing them in this form. Might be it is easier to remember. In a struggle between a power and an exponential, which one will dominate? Exponential is stronger than a power, if you want to memorize it. So in a struggle between a power and an exponential, the exponential wins. And in a struggle between a power and a logarithm, the power wins. Okay, and of course, in the struggle between a logarithm and an exponential, of course, exponential will win. This is a simple idea to prove this one for you. For example, if I have a positive number, for example, if a is positive and you have ln of x, which is a logarithm, and you divide it by x to power a, which is a power, and you take the limit, of course, x goes to infinity, I mean. Okay, so if you make x very large, in the battle between ln of x and this power function, the power function will win. It means that the answer becomes 0. Okay, that's what I meant. Okay, for example, if you want to see this proof of this one, they are not usually very easy, but for example, because x goes to infinity, let us concentrate on the interval from 1 and infinity. I mean, in principle, I want to use a squeezing theorem. So let me choose x to be greater than 1, for example. If that is the case, if x is greater than 1, ln of x is definitely positive. And because a is also positive, I multiply it, if I remember, because these things are technical, you have to do them. So you don't ask yourself how should I know to do these things? Yeah, someone has done it, we are repeating and reviewing it, okay? So if x is greater than 1, ln of x is positive. Because a is positive, when I multiply it by a over 2, you will see why a over 2, then it also becomes positive. Okay? So then, 0 is less than this number, because I showed you that this is positive. But then I can move this on top of this x. But there is an exercise which we didn't have time to go through. ln of any number, if that number is greater than 1, is always less than or equal to this number minus 1. This one is this exercise. That is not, by the way, hard, and the solution to this exercise is in the book. This example number 15, I am using it. Okay? So this becomes less than or equal to x to power a over 2 minus 1, which is definitely less than x to power a over 2. So I agree with you. All these calculations are, even though are understandable, but they are mysterious. The person who actually did it for the first time in this way probably was creative, and there we are following. So I hope that you understand that. So what I proved for you is that 0 is less than a over 2 ln of x, and this one is less than x to power a over 2. This I try to convince you about. And now what I do, I multiply everything by the reciprocal. This becomes 0, this becomes ln of x, but, this becomes 2 over a x to power a over 2. But I want to construct this. So I divide everything by x to power a. So this still becomes 0. This becomes ln of x, x to power a. If I divide this by x to power a, it becomes 2 over a x to power a over 2 in the denominator. So now you understand why I chose a to power 2. Yes? A over 2. A over 3 would also work. A over 4 would also work. As soon as, because I want to divide by x to power a, and my goal was to create some x in the denominator. Is that understandable? But now if I ask you what is the limit of 0 when x goes to infinity, of course the answer is 0. And if I ask you what is the limit of 2 over a x to power a over 2, x goes to infinity. Remember, a is positive. So what's the limit here? 2 is a constant, a is a constant, x is extremely large. A number divided by an extremely large number, the limit becomes 0. So the limit of the left is 0, the limit of the right is 0. So by squeezing theorem, the limit of the middle one should also be 0. Yes.
Where does the x to the power a divided by 2 minus 1 come from?
I told you, I skipped that one. So I am using this. I am using this exercise. If x is positive, then ln of x is always less than or equal to x minus 1.
Oh, okay.
Okay, I'm using this. And by the way, these kinds of inequalities, if I want to prove them, do you remember what was the trick? It was 2 lessons back. If I want to prove that ln of x is less than or equal to x minus 1, what was the standard method to do that? Do you remember?
Subtract to one side, take the
Yes, take the derivative and see if it is increasing or decreasing. But the problem here would be a little bit subtle, because the function might be increasing, decreasing depending on the value of x. So you have to consider 2 cases. Yes? Okay, so that is the standard. So I am taking this for granted because we don't have time. So this is why this works. If you have already proven this. Did I answer you?
Yeah.
Yeah, okay. So, but the point is that I haven't seen they ask you proving these things. I just want you to not memorize. I want you to see that if the limit is still a little bit problematic. If you have a hard limit to calculate, you have to be very creative. So at least I want you to know about these limits as well. Any questions? Okay, so this is the best, of course, we can do, but you have to practice on your own. So let us have a break for 5 minutes, and then we continue for today's lesson. Thank you.